Okay, so I'm going to talk about some research that we have done a few years ago, but given what happened this past summer, Chris thought it might be a good idea to kind of give you a refresher of using evaporative cooling to reduce temperatures in blueberries and to prevent heat damage. So as you know, heat damage is a prevalent problem in the Pacific Northwest, and it was particularly bad this past summer. We had a lot of damage this last summer, and what we learned, we already knew this, but this was reinforced that the damage can occur in early, mid, and late season cultivars, and it can occur in either green fruit or blue fruit. Now, traditionally, a lot of blueberry plants grown in the Pacific Northwest, primarily in Oregon, were irrigated by sprinklers. And whenever it got hot, they could run the sprinkler system to cool the berries. That worked great. So, but now things are changing. So we started to do some research back in 2014 by Dr. Joy Yang, who was a previous PhD student in my lab at that time, who did her PhD work on evaporative cooling. So she took a lot of measurements in the field using thermocouples, taking the temperature of the berries. She would connect the thermocouples to the fruit, record that information with the data logger. And here's a typical set of data that she collected in a field that was sprinkler irrigated. So here you see the temperatures. The black line is the ambient air temperature. The red line is uncooled temperature, a temperature of an uncooled berry. And the blue is the temperature where the berries were cooled with the sprinklers. Now, in this case, the sprinklers were initiated when the temperature hit 90 degrees Fahrenheit, were run for 15 minutes and then shut off for 45 minutes and then 15 minutes. So basically 15 minutes every hour. And what you could see is that that clearly every time you cool or turn on the sprinklers for cooling, it did cool the berries a lot, about 20 degrees below ambient temperature. So it's a very effective method of reducing the temperature whenever it gets hot. So here's an example of what she looked at damage in a field of Elliott blueberries. And here's an example of the number of damaged berries that she got off of a plant that was either cooled with the sprinklers or just were not cooled. In this case, we're just irrigated at night versus irrigated at night and cooled during the day. And you can see with cooling, we had almost no heat damage in this field. And we now know that Elliott is a cultivar that is less susceptible to heat damage, but she focused on late season cultivars, thinking that would be the cultivars that would be most impacted by heat. But of course, now most fields these days are irrigated by drip, and we don't have the sprinklers anymore to use for cooling. So here she looked at also the amount of damage that she got with a drip irrigated plant. You can see there's a lot more damaged berries in this case, and estimating what that berry damage was equal to about a pound of fruit per plant, which comes out with a 2.5 by 10 foot spacing to about 1,700 pounds of fruit per acre were lost in this particular year from heat damage with drip, where almost no fruit was lost when we had sprinklers and used cooling. So we knew at this point that there's a lot more damage with drip, no surprise. That there were differences among cultivars. We were thinking that early season cultivars really didn't get much damage versus some late season cultivars, like Aurora, were pretty susceptible to damage, while others like Elliott were not. And that damage was worse when a heat event was preceded by cooler weather. And that's exactly what we saw during that June heat dome event this past summer. We had pretty cool weather up until the last few days of June, when temperatures got up well over 100 in many places. And that's when we saw a lot of heat damage. Now, we did have another heat dome event the following month, which really didn't cause nearly as much heat damage. So the question was now, that Joy had for her research was, does evaporative cooling with micro sprinklers work? So what growers have as an option now is, if they're irrigating by drip, is to install a second system for cooling. So they will cool with either with some sort of micro sprinklers that they install along the rows, usually every other row at a 30 by 30 foot spacing is typically what we see. So her question was, does this actually work as well as sprinklers? When is it needed? How long should you run your system for cooling? Are there any effects of evaporative cooling on fruit quality or the date in which the fruit are harvested? Like, does it delay the harvest date? Which cultivars need it the most? And does it cause any other problems such as flooding or diseases in the field? So her objectives were to determine the critical temperature at which cooling is needed, to evaluate systems and practices for cooling and determine the effects on fruit quality, and to identify the potential problems associated with cooling. So here are some measurements that let me show you here. So here's what she did. She had these fine wire thermocouples that she glued to the berries. What she did is she inserted the tip of the thermocouples just below the skin, put a drop of glue, that held it in place. That's connected to a data logger, and that way she was collecting temperature data every minute on a cluster of blueberries. So here, what we see is were 3 heat events in 2015 in a commercial field of Aurora in Salem, Oregon. So on July 1st to 2nd, July 18th to 19th, and July 29th to 30th. And what she found was on these dates, when we had these heat events, the temperature of the berries were about 10 to 22 degrees higher than the ambient air temperature. So even though air temperatures were about 90 to 100 degrees, our fruit temperatures went from 105 to 120 degrees on those dates. So to get an idea of what were the temperature thresholds in these late season cultivars, she created these convection heat units that were designed originally by Julie Terrara, which were basically a heating element connected to the data logger, a fan that would blow the hot air into a cup that was placed directly beneath the fruit. And with these heating units, she was able to control the temperature of the cluster. So here's an example of one of her data sets where she controlled the berry temperatures either at 108, 111, 115, or 118 degrees Fahrenheit. And she did this test in both Aurora and in Elliott. And this was the results of that study, where she looked at the heat damage within a cluster on both green and blue fruit of Aurora and Elliott. So on the upper left here was the worst case scenario, green Aurora fruit berries. And on the bottom right is the best case scenario, blue Elliott berries. So basically, if you look at the graphs, you can see that the dark circles with the temperature controlled at 108 degrees, the white circles 111 degrees, the black triangles 115 degrees, and the white triangles 118 degrees Fahrenheit. And what she wanted to know is, when you held the berries at these temperatures for a certain amount of time, when did the damage occur? So what she found, what you can see here, is that in Aurora, when the fruit were green, the damage occurred in as little as 2 hours at 100 degrees Fahrenheit. So at a fairly low temperature, and that's berry temperature, not air temperature. And when the berries were blue, they were more tolerant of heat. In this case, they did not develop damage until 3.5 hours at 115 degrees. Now, Elliott was more resistant to heat and could tolerate 118 degrees for 1.5 hours when they were green and 2.5 hours when they were blue. So basically what this demonstrated, that Aurora was damaged faster and more severely than Elliott. And certainly this last summer showed us that this was absolutely the case. And she also found that green fruit was more sensitive to heat than blue colored fruit. I'm not so sure that was so obvious this summer, because we did get so much heat damage, but we certainly did see a lot of damage in both green and blue colored fruit. So she also looked at what was happening at the food, in the berries themselves at the structural level to try to understand why blue fruit were less susceptible to heat damage than green. So on the left was a cross section of a berry skin. So on the top, the W is the wax layer, the C is a cuticle layer, so that thin layer just below the wax, and the E is an epidermal cell. So this is a row of epidermal cells on the surface of a berry. And this was taken with an electron microscope. And on the right are the surface of the berries. Here's a green and here's a blue. So here we're looking at the wax, and you can see when the berries are green that the wax is actually more of a crystalline structure, whereas once they turn blue, that wax becomes more amorphous and completely covers the surface of the berries. And looking at a cross section, you can see also that that wax layer and that cuticle layer become thicker as that berry matures. So blue colored fruit have a thicker layer of wax than green fruit. And so that is going to help protect that fruit once it starts turning blue. And the other thing that she found was that the wax development increased when the berries were at a higher temperature or were sun exposed. So if you have fruit in the sun, they tend to develop a thicker layer of wax. So consequently, when you have cooler days, they aren't developing this protective layer of wax as well as they would otherwise if it was a hotter day. So when you go from a cooler day to a hot day, consequently, you get a lot more fruit damage. So the bottom line, what she found from these studies was that you want to begin cooling when air temperature reaches about 90 degrees Fahrenheit, and that corresponds to those berry temperatures where she saw the damage during early stages of fruit development. And you want to start cooling around 95 degrees during later stages. So you could hold off a little bit longer once you get into later stages of fruit development. So her next question is, what is the efficacy of cooling with microsprinklers? So again, she looked at 3 days, 3 cooling events, not 3 days, but 3 cooling events during the summer of 2015 in this field of Aurora, where temperatures got above 95 degrees at this particular site. And here she had the berries that were uncooled, and this was basically 3-acre plots that she had that were uncooled versus a 3-acre plot in purple here, where she applied the microsprinkler cooling continuously whenever it got to 90 degrees Fahrenheit. So you can see here that on the first day in July 1st, where the air temperature, once it got above 90 degrees, she turned on the cooling system, and you can see it quickly dropped the temperature of those berries. And that happened basically every time that we had a heat event. It was very effective at cooling the fruit. In this case, you can see it's a little less effective here, and that has to do with the humidity. When it's drier, when you have a lower humidity, it tends to be more effective than when it has higher humidity. On this date, it was not only hot, but it was also a humid day. So the cooling was not as effective, but still much cooler than the uncooled berries. So continuous cooling reduced the temperature of the berries by 20 to 26 degrees Fahrenheit using these microsprinklers. So that was great, but she did notice some problems with using these microsprinklers continuously. One is it was putting too much water on the field. Basically, she's putting out about 1/10 of an inch of water per hour on the field. So there's quite a bit of water going onto that field. She also noticed that when you had continuous cooling, when you come out the next morning, there were a lot more slugs in those 3-acre plots with the continuous cooling than in her other plots, which also brings the question, is there greater potential for fruit rot? Now, we didn't really look at that in this case, but we could certainly think that if you got more water on those berries, you're going to have more potential for fruit rot. And then the other thing that she noticed too, that obviously that field is a lot wetter. So when you try to get in the next morning for fruit harvest, it's more difficult to do because you got to wait for those plants to dry out a little bit. So the other treatment she looked at was cycling that cooling system. So in this case, she would turn, once it got to 90 degrees Fahrenheit, she would turn the system on for an hour, then turn it off for an hour, on for an hour, off for an hour. And in this case, Of course, every time you turn the water on, it cools the berries, but as soon as you turn it off, it goes back up to the ambient temperature. But you're only, to the uncooled temperature. But you're only reaching that temperature for a short period of time. You're not maintaining those berries at a potentially damaging temperature for an extended period, because it's not just a matter of reaching that temperature, but it's reaching it for an extended period of time, usually at least 2 hours of time. So, and then her fourth treatment was a treatment where she did continuous cooling in 20-minute cycles. So basically on and off every 20 minutes. And in this case, you can see it was even more effective, where even though you're using half as much water, you're still reducing that berry temperature considerably with the cooling cycle. Now, one thing that she also did was look at fruit quality. Now, because this was in a grower's field and we had 3-acre plots, you couldn't really replicate that. But she did take the measurements and just sort of wanted to get an idea, was there an effect on fruit quality in the field? Now, Brix was sort of all over the place. There might have been some effects, but there was no obvious trend. Titratable acidity, not much effect. But one thing that was consistent was that the berries that were not cooled were softer than those with any of the cooling treatments. So clearly cooling increased the firmness of the fruit. So she wanted to take that a little bit further and actually do this in a controlled study where she had replications and see what the effects of cooling was on fruit quality. So she went to one of our research plantings in Corvallis, where she controlled cooling using our microspray systems on smaller plots. So she did this both in Aurora and Elliott. In this case, this is the percent fruit damage. We didn't have a lot of fruit damage this particular summer. This was 2016, or 2017, excuse me. But you can see that in both Aurora and Elliott, we had significantly less fruit damage with cooling and no cooling. But it really wasn't that high this particular summer. But what we also saw were some significant effects of cooling on fruit quality. So wherever you see a star here on their significance, so cooling for berry weight, Brix, and firmness was significant. And with firmness, there was also an interaction between the cultivar and cooling, indicating that one cultivar responded differently to cooling than the other. So if we look at berry weight, we could see in Aurora that the berries were heavier when we cooled the plants than we had no cooling. This was also the case with Elliott, but not quite as dramatic as it was in Aurora. Brix was also affected. In this case, was lower with cooling than with no cooling in both Aurora and in Elliott. And we would expect that based on the berry weights. When you get a larger berry, you get more water in that fruit, so that tends to dilute the sugars in the fruit, so you get a lower Brix reading. But what we also saw was that, again, that firmness was significantly higher with cooling than with no cooling. But in this case, it only happened in Aurora, where Elliott, there was no difference in the firmness, whether we cooled or not. So Aurora, which is very sensitive to heat damage, had the biggest benefit from the cooling in the study. So basically, you're left with 4 options with regards to dealing with heat damage and heat events. The first option, of course, is to not use cooling. That's going to save water, and it's not going to have any additional system costs. But as we saw this past summer, you're taking a gamble that you're going to lose some fruit and reduce fruit quality. And a cultivar like Aurora, I don't think you'd want to grow Aurora at this point without some sort of cooling system. Now, your second option is to run your system continuously whenever it gets hot. And that is very effective at reducing the berry temperatures, but it does also tend to use a lot of water, and it causes problems with pests and diseases, and will also interfere with your harvest if you're doing it right, during a harvest period. So an option to help with that would be to cycle your cooling. So with the 1-hour cooling cycles, you can basically rotate between 2 blocks, have 1 block on, 1 off, and then switch. Now, your berry temperatures may increase above critical temperatures between cycles if you wait as long as an hour. So we think the sweet spot is somewhere between 15 to 20-minute cooling cycles, which again is going to save water. In this case, a 20-minute cycle, you can rotate among 3 blocks. And but you have to be careful. You don't want to go too short with the cycles because you want to give your system enough time to fully pressurize as you go from block to block. So the final part of her dissertation was to develop a model for predicting berry temperatures and for scheduling evaporative cooling. So basically what she wanted to do was to take weather conditions and predict what effect that's having on berry temperatures and able to use weather information to decide when to turn on a cooling system. So she developed a model that was able to do that based on measurements of solar radiation, air temperature, wind speed, relative humidity. She took in consideration the size and shape of the blueberries, any ground cover, whether you have grass or not, the temperature of the irrigation water, and the flow rate of the nozzles in the micro sprinkler or sprinkler system. And the model was pretty good. She had a very good correlation between her, here's the dotted line is the air temperature. The dashed line is the actual measured fruit temperature, and the black is the simulated or modeled fruit temperature. And you can see they're very close over the course of the day. And if you look at it here during a cooling cycle, again, you can see the solid versus the dashed lines, the measured versus the simulated. They're very close. So the model is very effective for predicting berry temperature. So the idea is that you combine this model with a forecast program to predict heat damage on any given day. And it could be a tool for making cooling decisions and evaluating best cooling practices. So for example, here she did some simulations. So rather than actually doing a study now, what we can do is we can run this model to see what would happen under various conditions. So for example, she looked at the difference between increasing the water temperature from 20 to 25 degrees Celsius, which is basically 68 or 77 degrees Fahrenheit. And what you can see is that the red is the warmer water temperature for cooling. And you can see that it's less effective, but it's still pretty effective and pretty close to what it was at 68 degrees Fahrenheit. So water temperature does have an effect, but not a huge effect. So that doesn't seem to be a huge concern. And here's an example with the continuous versus the cycled cooling. And again, you can see with continuous cooling, you're reducing that berry temperature throughout the course of the day, whereas with the cycling goes up and down. But these short peaks where that temperature rises, we now know really doesn't impact the fruit at all. We don't get heat damage from when these temperatures just get up to a critical temperature for a few minutes in a short period of time. And then the third scenario that she looked at was to reduce the rate of water applications by 33%. So basically using a system that has a smaller size nozzle, so putting less water on. And that seemed to have the biggest impact on the berry temperature. So by reducing it by just 1/3, you can see that the fruit temperatures got quite a bit higher than they did with the standard that she had for the model. So this tells you that's very important that you have a properly designed irrigation system. Otherwise, you're gonna not do yourself much good by applying water because you're gonna get above those critical temperatures between your cooling cycles. So what we're doing now is we're taking this information, we're trying to develop a sensing system that we can put into a field, an inexpensive system that basically will automate the evaporative cooling system in the field. So the idea is it consists of an all-in-one weather station. And this is some work that we're doing with Troy Peters and Lovecott and Prosser. There's a thermal or imager to look at the temperatures. They've developed it for apples, and we're seeing if we can use a similar type imager in blueberries. You connect that to a control unit, and you couple that with the model that we have that we know what the temperature thresholds are. Tells us when to turn those systems on to prevent the temperatures from getting too high in the berries. That's hooked up to an automatic valve that runs your micro sprinkler. So the idea is here we have an automated system that you can use to basically run the evaporative cooling when needed. So what's the next step for us is to construct these sensing systems for blueberries and evaluate their use in commercial fields. And we're thinking about doing this in Eastern Washington in a field of Draper. So looking at a late season cultivar in Eastern Washington should be a worst case scenario. And if it works there, it should work anywhere else. Now we're also looking at other things that might help reduce heat damage. Obviously, if your plants are water stressed, they're not going to have as much transpiration. And if they don't have as much transpiration, they're going to get warmer and you're potentially exposed to more heat damage. You also have less canopy. So we're looking at pulse drip irrigation. So we've been doing some studies to see what happens if you irrigate in short pulses rather than in continuous applications. And we've shown that pulsing will actually increase yield in Draper blueberry in a study that we're doing in Eastern Washington. And we're also looking at better tools for monitoring plant water status of the plants and to prevent water stress during heat events. So some things we're doing is we're using drones and remote imaging to look at the water status of the plants. And we're also working with the group in Cornell to develop a microtensiometer, which is basically an instrument that you hook up to the blueberries to see what the water status is. So we have some other projects in the works where that will hopefully help out with evaporative cooling in the future. So if you're interested in additional information on this topic, we have published the research from Joy's dissertation. They're available in Hort Science, but if you're curious about this, you can go to my website, just search my name, USDA, and my publications will be there. And you can find these 3 papers, one on critical temperature and heating times for fruit damage, another on thermal cooling with sprinklers and micro sprinklers, and the third on the energy balance that we developed. So the collaborators were, of course, Joy Yang, who did this for her research, Bernie Strick, Brian Yorgi, and Yan Zhao, Troy Peters, Love Cott, and Chris Thomas, as well as technical support from a bunch of people, as well as John Humble from Fall Creek and Benito Mendoza from Arbor Grove. And then I'd like to acknowledge funding from both the Oregon and Washington Blueberry Commissions who provided a considerable amount of support for this project. Thank you for that. So I will stop there, and if there's time, I'll take questions. So I heard some question about other varieties, but I don't know what and I heard blue crop, but that's all I heard. Okay, so if I understand what the question is, do we see heat damage in other varieties like blue crop and Duke? And yes, we do. I mean, we did see that this summer. They seem to be not as sensitive. Well, Duke, it was hard to say. At least in Oregon, a lot of the fruit that was fully exposed to the sun had been picked prior to the heat dome event. Now, maybe in Washington, you guys might have not been in that situation. So you might have seen more damage than we did. But yeah, certainly we see that any cultivar has potential for heat damage. And it really depends on what stage of development they're at when that heat dome or heat event occurs. So the question, how does a harvester, is that, well, it's fine with as far as the evaporative cooling with the micro sprinklers. They're down low enough where the harvester can get over the top of them. That one field where we did the research in Salem, they do both pick by hand and use a harvester. So yeah, it's perfectly fine to use a harvester with, and have a micro sprinkler system in the field.
Thanks, Dave. Appreciate it, and look forward to seeing you in person, hopefully next year.
Yeah, it'd be great. All right. Well, thanks, everyone. It's good to see. It's good to talk to you. Not see you, but talk to you.